have Jon Rasiko from DeepCode, CEO. Jon Rasiko is a cybersecurity and intelligence consultant with more than 25 years in the field, currently partnering with DISC for its advanced research program. Outside of cybersecurity for space systems, Jon is CEO of DeepCode, which specializes in cybersecurity and intelligence services, including tactical cyber operations, reverse engineering, vulnerability assessment, cybercrime, and malware research. Jon has been involved in computer security since building his first freaking boxes in the early 90s, and has since then did everything between penetration testing to vulnerability assessments of weapons platforms during his time in the Canadian Armed Forces. After entering the private sector, Jon joined the HackerSat Capture the Flag, studied security of machine learning algorithms, and continues to explore and understand the leading edge of cyber warfare. We also have joining him Nicholas Scheurkogel from DISC. Nicholas Scheurkogel is the CEO of DISC and leads the consulting services, strategy, and innovation capabilities. He's over 19 years in the IT and cybersecurity industry, where he has led a high-end cyber intelligence teams for the Government of Canada, national and international cyber capability, to develop efforts and provide advice and guidance to governments and high-value corporations. A recognized innovator in the field, Nicholas has pioneered cyber capabilities, including partnering models, cyber tactics, national strategies, and operational concepts. So with that, it's my pleasure to hand over to you, Nicholas.
Good afternoon, everybody. Thank you for making the time at the end of the day to come and see us talk. We're very happy to be here today. So today we're going to be talking about attack taxonomies, and specifically how the attack taxonomy can be built into or can be used to develop indicators of compromise and then help with the validation of security systems and the design of security platforms in the space environment. So things we're going to talk about today, things like spoofing, spoofing, hardware attacks, software attacks, jamming, and a range of attacks that Jon here will go after. Next slide. So who we are specifically, again, DISC is a niche cybersecurity firm based out of Ottawa, Canada. We have won a number of grants and contracts for the development of niche cybersecurity platforms in different areas, one particularly in space, which is our monitoring system, onboard satellite monitoring system. We also do work in are developing architectures and identifying new types of functionality that will help the security implementation within satellites. So not always, are these satellites traditionally engineered to be internally monitored. So when you try to go down this road, there are a number of things that you may want to do to be able to allow your system to be, more effectively monitored. In terms of our solution, it's called the Eclipse. This is an onboard satellite monitoring system. It's low power, lightweight, optimized for the particular platform that it's on. And the work that we're going to talk about today was sort of the precursor that allowed us to then customize and understand the things that we needed to see within that environment. So just with that, because I want to get to the fun part, which is Jon's. So Jon, this is going to present the rest of the presentation, which is the what we engaged Jon to do as part of the DISC Space Lab.
Just go back a little bit to fight back the log mode. All right, so I'm Jon. I'm from DeepCode. Today we are going to present you the research we have on actually attacking the space segment of the satellite systems. So first, before we get there, I think it's important to add some context on why we're doing this, what's the motivation, and what we want to achieve with this. So since you are here, you already know that there's a thing that's catching on right now in security for satellites. Wasn't always the case, though. It kind of came up 3 or 4 years ago, where suddenly cybersecurity for satellite became a thing. So we talked between ourselves, say, okay, what's going on here? Why is suddenly people want to secure satellite? And okay, how do we defend satellite from hackers? Well, the first question that we start asking ourselves is, okay, how do we attack satellite? It's not very clear on how we do that. So we start doing some research. There was some very good paper out there. But one thing we noticed is that either it talks a lot about the ground station, which is fair. I mean, it's a very real target. There was a lot of talk about the data links also. And the other issue we kind of had back then is that when they were describing attack, it was either very shallow, like very large category of, yeah, we can do social engineering, yeah, we can set up bad firmware. Or it was very, very technical, like we could find a thesis, a 500-page on targeting a very specific system. But it seems like there was a gap between both of them. So how do we actually reconcile both of these things and have a full chain of attack that describe how we can actually target the satellite? So we went on and started looking at what was going on with this. So it's not secret, I think pretty much everyone here knows that there's a change in the satellite industry, right? We're going from old space to new space, from government only to pretty much everyone in the private industry can have access to satellite technology right now. There's a big downward pressure for the costs of launching a satellite and building one, and makes the things a lot more accessible to a lot more people like me, cybersecurity researcher who had no prior knowledge of satellite. And it seems that what's happening is because now everybody can look at this, it seems the only security measure that was in satellite is fading away, and that was security by obscurity. Before that, as far as I'm concerned, there wasn't much security on this. There was very much the same issue as the industrial systems that we had. And a good example of this is actually the good people at Iridium. 2007, they famously declared, well, the interface is really complicated, nobody's gonna figure it out. And 8 years later, well, you had security researcher at the Chaos Computer Club actually releasing all the information on how it could work. And to add insult to the injury, well, the presentation of Iridium was leaked on WikiLeaks. So security by obscurity, it's not that thing in 2023, really. So that's to take in consideration, because there's a lot more visibility into it. Well, there's a lot more incidents going on and being reported. And these are just a couple of examples that we used to read about when we were designing our attacks on the satellite system themselves. Now, the interesting thing, though, is that all segments of the satellite systems are not targeted equally. So based on some research, actually, we find out that there's a growing trend of successfully attacking the ground station, the data links, but there's not much happening on the payloads themselves. And we decided, well, that might be an interesting thing to look at before it becomes a problem, right? So that's where we decided, okay, let's look at the space segment, see how we can attack this. First, we need to figure out who is attacking the satellite. Is there anyone attacking it? Or is there anyone who wants to attack this? So we look at this and we decided there was kind of 5 major categories of threat actors that we need to consider when we design our attacks. The first one, state-sponsored actor. So your government agencies or your commercial agencies that are sponsored by government department. These usually are very resourceful, a lot of technical knowledge, and in our opinion, it's one of the threat actors that's the most likely to target the space segment because they have a purpose for it. Next one, criminal organization. From what we read, mostly interested in the ground station. I'm sure there's a lot of money to be made in ransoming ground station. If you cannot operate a satellite, you're going to pay a lot of money to get it back, probably. Next one, we considered groups based on ideology, politics, terrorists, religion, whatever. What we've seen from them is mostly interested in the data links because they are interested in broadcasting their message or their intent. They might be interested in the ground station also. But we don't expect to see them on the payload anytime soon unless they have an opportunity to do it. Next, your activist, your group, your lone hacker who's doing it for the lulz or doing it for the fame, for the reps, street creds. Not a lot of resource, but can be very determined. But so far, mostly the ground station for them. Finally, the last one, often underrated and one of the most dangerous, is the insider. They're all over the supply chain. They have access, trusted access to all the components, and they can be co-opted by any of the other threat actors if needed to. So when we design our attacks, we actually take all of these actors in consideration to see how we can go about it. Okay, so we designed the who. We have an idea of who we want to protect against, right? the next step is, okay, so how did you do it? How can we figure out how they're going to attack the satellite system? Well, the good thing about the space segment is that you have a very limited set of entry points. And most of the time, it's going to be the transmitter or the radios. Either the one for command and telemetry, the one that's on the payload, or, well, actually, that's pretty much it, right, in terms of transistors, transmitter, as far as I know. And I don't know much. And how you access the transceiver? Well, you can have a compromised ground station. It's the most likely one. You can have a rogue ground station if your data link is weak, if you stole the encryption keys, or you figure out somehow. That's a possible way to get into the radio. You can have a compromise or rogue user terminal that somehow can access the transmitter on the payload system. Or you can have satellite to satellite, either a compromised constellation or maybe even compromised satellite that you can figure out a way to connect to the other one. And how you can do that? Well, you can have software vulnerability in your radios that allows you to smash the stack or whatever. There's a bunch of ways to do this. Other way, supply chain. Well, you have a hardware backdoor. You have a chip that activates based on a logic pump. That's another way you get into it. And one of the more maybe academic ways through a sensor. It's been shown sometimes, at least at the academic level, that you can send some specific waveform to a sensor that either push wrong values to the onboard computer and can do some stuff, or can actually find a way to smash the stack on the sensor and run some code on the sensor itself. But it's very complicated. So this one's a bit on the back burner for now. Now, you got into your spacecraft. Well, it's time to move around, right? And where can you move around with this? Well, it just happened you have a bunch of subsystems. And each of these subsystems have chips, they have processor, memory, some of them have file systems, FPGAs, you have interface. Sometimes you have a lot more code than you think you have on your subsystem. You injected an operating system for a third party, might be doing things that you don't know what it does. So anyone who attacks your space station can move into these things. And all of these subsystems are connected to a communication bus, usually. 15 to 53, CAN bus, whatever, or maybe sometimes it's just they have shared memory. Sometimes it's just a PCI connector. And then you can maybe leverage a shared memory to move around if you want to. That's a way you can do that. Now you're doing all of this because you have a purpose in mind. Either you want to trash the satellite for some reason, or if you're a bit more sophisticated, well, you want to steal data out of it. You want to do some SIGINT. Maybe if you're really into it, you want to modify the data directly on the spacecraft so it can be downloaded and used for malicious purposes. Now, I know I've been through this a little bit quickly, but it's time to put all of this together, right? We insert the why, the who, and the what you can do. But it's time to put this together in a format that we can share and easily describe together. And maybe some of you are seeing where I'm going with this, but it just happened that we have the MITRE attack framework that's pretty good to put all of this together. And that's what we did, actually. So just to make share quickly what's the attack framework. It's a way to describe cyber attacks against a computer system, right? And the way we do this is usually by dividing the attack into specific phases. And for each phases, we're going to define a technique that achieves this phase. And for each technique, we're actually going to go and define some specific abilities that are relevant to the environment we're using. So this is an example for industrial systems. And to further explain a little bit how it is let's say you want to, for example, exfiltrate passwords from a compromised system, right? So you would have in the collection phase a technique that says exfiltrate password, and in that technique you will have different abilities, maybe for Windows, for Linux, for whatever environment you're using. Now there's already a bunch of metrics defined. One for traditional computer system, which could be used for translation, one for mobile, one for industrial system. And until today I didn't know, but there was none for satellite. That's changing very quickly. So we define our own. All right, I killed the Am I good? All right. Oh, there's a difference now. Did anyone didn't hear me in the back, or? All right. So anyway, we define our own matrix. This is by no means the end all of all matrix. Actually, we talked to some great people today, and they showed their matrix, and we're certainly gonna leverage that for sure. But the point we're trying to make here is that we need a common way to share and distribute our attack information on the space system. So in our case, we divided it into 9 phases, and we developed different techniques for it. And what we did, well, actually, what I'm going to is that the biggest advantage of using this kind of matrix, it's first, it already exists. We don't reinvent the wheel, and we can implement it. And that's actually what we did. All right, last pictures. So how can we actually implement this to define indicators of compromise into our space system? And we're going to show you how we did it using Caldera and NUS3. So first, NUS3 is actually a free satellite, a small satellite simulator developed by NASA. Free open source, highly customizable, has a nice little visualization tool. It has a ground station, and you can actually customize it by implementing custom apps, so we can simulate a rogue device or a supply chain attack using this platform. We chose this one because it's the one that was used in the first CYSAT competitions challenge. So we stick with it since it was free and open source. So anyone can actually use it, very easy to install. Once we define an environment where we want to simulate our attack, we're going to go back to our matrix that we used before, and we're going to actually implement the abilities for each technique to actually execute into our environment. So if it's not relevant, we can remove it. But if it is, we actually find a way to script it and connect it to the NUS3 environment. And for that, actually, once you have all your techniques implemented, well, it's very easy to start selecting scenarios that you want to test on your satellites. So in this case, we're going to use a very basic example just to cut time. But we're going to decide that we're going to simulate an activist that has access to a compromised ground station, and he wants to trash the satellite by causing it to lose control over it. In the meantime, he's going to try to erase his tracks, like by disabling the login or disabling event filtering on the space station. Now, we can actually implement this attack using a tool called Caldera. So it's an open source tool developed by MITRE, in which you can actually define your adversaries. In this case, we're going to implement an activist. And we actually link our scripts to communicate with the NUS environment into a specific sequence of event that's going to take place. And Caldera is going to execute all of these steps for us to simulate our attacker. And we can launch it. It's going to execute automatically, one by one. You can also do it manually if you want to review what's going on. And at the same time, while this happens, what we're doing is we're monitoring the telemetry on the simulation environment. So we're monitoring performance indicators, telemetry, and we're trying to find these weird change into the telemetry to use as indicator of compromise. So in this state, in this case, very simple example where we just simulated a denial of service using a command flood. So we just flooded a bunch of commands via the ground station. And of course, what you're going to see is if you have a command counter on your spacecraft, it's going to go up very quickly. So in this case, we can say, all right, within 1 minute, the command counter increased by 100. So you're having a command flood right now. So we can go back and define, okay, if we have an increase of 100 comments in 1 minute, that's an indicator of compromise. And we can define mitigation, saying, okay, maybe you should implement command throttling in your spacecraft. Again, basic example, but we can use it for more complex attacks. And we can actually recommend that the developer of the satellite, add some kind of indicator of compromise. For example, if you want to monitor a memory, we can actually monitor a change in the memory for backdoors or exploits. All right, so where are we with this? So actually, right now, we're implementing this into a high fidelity environment for one of our partners that actually operates a satellite for their living. And we're actually developing, implementing all of these techniques into their environment and testing them to see what kind of indicator of compromise we can get from their simulation system. Once we get that, we use these indicators to develop our monitor system that we want to test and make sure that we cover our areas. Eventually, what we hope to achieve is to provide a set of tools, service, and process that can be integrated directly at the design phase, implementation phase, so that the developers can run their code, compile it, run it in the simulator, run the attacks, and see if their mitigation services are working or if they're missing some. This way, right at the beginning, you're kind of covered for the risk that the USS is targeting your satellite. And yep, I think that's pretty much it for now. Of course, I know I'm the only last guy between you and the snacks. So, but if you have any question, feel free to do so. Otherwise, feel free to email us. We're gonna stick around also if you want to talk to us. Thanks for staying. Hope it helped. And we're certainly hoping that more people will start using this kind of framework to share and describe their attacks. Thank you, everyone.
Thank you, John and Nicholas. Very interesting work. So do we have any questions in the room? Okay. If not, I also don't see any online yet. Maybe one question from my side. Okay, and then I'll go to the gentleman in the room. When you execute these, so you say you have a customer and you're executing these, emulating, let's say, these attacks actually in their systems so that they see the results. When you define these attacks, how generic are they? Do you have to customize them each time for the specific customer system that's under attack, or can you translate, let's say, the matrix you've come up with to also generic attack scripts or tools?
So there's always a level of customization because there's still difference in the way they implement their simulation environment. So sometimes it's fully virtual, sometimes it's not. Sometimes they use R, sometimes they use MATLAB. So the way we interface with them and their simulation environments, it's always different. And also they don't have all the same components, right? Some have a different star sensor, some have no star sensor. So we adjust based on the partner or the customer we have.
Okay, thank you. So there was a question in the audience.
Thank you for your presentation. I was wondering, what are your plans to do with supply chain?
So supply chain, the thing, one way we can do it is actually like for Nustry, we can actually develop our own module, right? So we can integrate it into the bus and simulate supply chain attack this way. It's not ideal, but it's a way to do it. And it's the same logic. So we can implement a logic bomb, or we can credentials, memory, and stuff like this. So that's the way we do it for now.
Nice, cool. Thank you.
Thank you.
On the TTPs that you had in the matrix, so how much data is behind those? Like, is it just the title, or like is there robust descriptions of what each one of those kind of means?
So we use some pack that already exists, right? So some of them are similar. We're not going to reinvent the wheel. Otherwise, some of them are customized for some specific environment right now. So we don't have a full-fledged, pretty much like you at the one you have, right? We're focused on the implementation. But usually it comes with a basic description that match what the environment we're testing right now.
Any more questions? Yes.
Have you considered anything related to electromagnetics or laser attacks or anything like that, or is that sort of out of scope of your work?
No, that's out of scope for us. We want to focus on cyber.
Okay.
It's not our expertise to go outside of layer 1 stuff. So.
No worries.
Okay, one question online. Have you looked into integration with the Sparta framework in addition to MITRE?
Yes, we actually just learned about this today. So we're certainly going to look at this more deeply to see if we can complement what we have or how we can integrate with that, that's for sure.
Yeah, I think Sparta is also based on attack type standardized representation. So, yep. Another question online. Do you rely on the telemetry for the detection of attacks? If yes, how will it work in a highly autonomous system, limited telemetry?
Now, are you talking about the actual monitoring platform or the simulation activity?
This is a good question.
From the monitoring platform perspective, like, we're clearly not going to divulge exactly how we're doing the internal monitoring of the solution that we have. But we're happy to discuss that with customers and clients and potential partners. Yeah, it needs to do more than telemetry.
And in terms of simulation, is that we're going to generate, when possible, a new indicator to see if it works at detecting the attack, if there's no telemetry available.
Okay, hope that answered the question online. Any further questions in the room or online? Yeah.
So, kind of on the detection scheme. So I didn't see much in the presentation, which it wasn't really meant for that, on the kind of onboard detection. So it seems like what you're doing is more of a test-driven development from like simulating TTPs to help derive what type of detections that you have on the vehicle, right? So like, what do you have any literature on like what are the IOCs and how you derive IOCs from like from an onboard perspective? I know you said like, I guess that's some of the secret sauce, but is there any published literature or anything that you've done that people could read is like, oh, well, these are indicators, like you said, well, you got 100 commands in 1 second. That's a command flood. That's an IOC or a TTP detection. Do you have anything published like that other people could benefit from?
No, at this time we don't, because we're still developing them, and I don't want to develop something half-assed. So I'd rather like have a full test in a full environment, saying, okay, this is what we did for this basic environment. But at this point, I'm not confident enough to say, yeah, we found everything, or this is the definitive list of what we have.
Yeah, because we have research in that exact area where we're running these TTP simulations on vehicles with onboard monitoring, and then trying to see if it can detect that, and then changing the IDS to be able to detect it because it missed it. And then it's a continual evolution, because we don't have, like, it's in the Windows world, I think it's easier because we have 30 years of attacks to look at, but in the space vehicle world, we don't have as many.
And in the other issue is that the target system is always a bit different from each other, right? So 100%. We cannot have a definitive indicator. Maybe for some system 100 is fine. Maybe for others that's way overkill. So there's a kind of a general rule maybe we can write about, but not a very definitive list of indicators, I think.
So when we start working with a customer, we started with understanding what the satellite platform is, what it does, who owns it, who are the individuals that, you know, are adversary groups that may want to attack it. We then build a range of likely attack scenarios, because we can't monitor for everything. That is not feasible. We have to find what are those things that specifically need to be monitored, and what's the cost benefit of the activity to do that monitoring in that particular environment. So for any application, those specific indicators of compromise are developed through an engineering process in the requirements phase, so that, you know, we understand what we need to monitor, but also what are the architectural changes that I mentioned at the beginning to make that platform more monitorable. Some of them are very easy, some of them are very complicated. So, and that's that process that then gets also fed into how you then monitor and instrument, and then take that information at your ground station. We can definitely talk more about that at the booth we have over in that far corner, if anyone is interested in having a more lengthy discussion on it.
I was hoping you had an easy button that you could just...
we forgot it in Canada.
Detect all the attacks.
I'm sorry, we were relying on YouTube, right?
Yeah, they didn't allow us to bring it up. So.
Okay, with that, thank you very much, guys. Very interesting. Give us a good hand.